Okay, let's make a start then. Cool. Yep, so this one's going to be the review class for the last couple of topics that we're having a look at, namely a bit on the solving and graphing of exponentials and the remainder and factor theorem from polynomials. If there's any preferences on what we should focus on as far as when we get into the actual questions, happy to take that. But for now, because I believe the factor remainder theorem, I don't know if everyone here has been part of that class, but this should all be stuff that you've probably already seen. I'll go through it at a relatively fast pace. If it's too fast, I'm more than happy to slow down. But yeah, since this is mostly second time looking at it, I figure we could probably do it a bit faster and save some more time for questions. Okay, so polynomials, remainder theorem and factor theorem. What are we doing here? Well, it is simply an equation that can help us find the remainder after division by some linear. So we start with some polynomial, in this case a cubic. Dividing it by a linear is going to create some remainder. That remainder might be 0, but it is still a remainder. The equation is simple. You just need to determine what your b and a terms are. That's going to come from the linear itself. So the linear is ax plus b. That means in this case the a is going to be 1, since that's the coefficient on the x, and the b is going to be negative 2, since that's the constant. That gets you your a and your b. The f of x is always just the polynomial that you're trying to divide. So sub in, simplify, simplify, simplify. You get your remainder. Any questions so far? Cool. You can use this in not necessarily obvious ways. Like for instance, if the remainder is part of the known information that you have, then using the remainder theorem might not necessarily be required to get the remainder, but it can be required to get some other unknowns in perhaps the polynomial, for instance. This is a pretty typical textbook question. So you got your a and your b coming from the linear, you got the result itself, the 17 from the remainder, and then you've got the whole polynomial. So once you get your terms and sub them in, you'll realize that the only thing left over is the coefficient, and so you can rearrange to solve that coefficient. The more applicable, or the more likely case in like a SAC, for instance, would be the factor theorem, which is just a special case of the remainder theorem. It's simply what you get when the remainder is 0. Remainder 0 proves a factor because by definition a factor is something that's perfectly divisible into the term that you're dividing. Just got a quick question. Hi, I have a test coming up on Monday on all the content here. Well, that's good. It's all the content here. Would really appreciate it if I could go over the content listed below after we revise. Cool. Okay. Yeah, I'll have a look at that. Sure. Okay, so proving a factor, that's one of the textbook type questions. It's just prove that this is a factor. So chuck it into remainder theorem. If you get 0, cool. If not, then, well, if you don't get 0 in a question like this, it's more like you've done a working out error there, because you should always get 0 for this. If it's prove whether or not this is a factor, then that's going to be determined based on whether you got 0 or not. More specific, more likely is going to be to actually find a factor. So here's how we can actually apply factor theorem into solving these more complicated polynomials. The cases that you'll be given will always have a leading coefficient of 1, and under those circumstances you follow this verbatim. Start by looking at the factors of the last term, the constant specifically. If the constant's 0, then you would factorize it by using just other methods of taking an x out, for instance. There's always going to be a constant in this case. So you listed all those factors. These are the things that you're testing by plugging into your polynomial. So 6 is going to have plus minus 1, plus minus 2, plus minus 3, and plus minus 6. Test those off in order of easiest to hardest. For 2 reasons. One is because the easiest ones are fastest to do, and the other is that your assessors are also trying to make it so that you're not spending forever testing, 8 separate factors. It'll take quite a while. And so they make it easier enough to make sure that when they're writing it, it's going to be one of the earliest ones. I can't imagine you ever doing more than like 3 separate substitutions before you get to your factor, in a SAC scenario anyway. In the textbook, they might be nasty because the textbook. Yep, so basically you're testing the factors until you get 0. Well, you're testing the possible numbers, so until you get 0, because that will prove that you have a factor. Under this simplified circumstance, you pretty much will always take a equals 1. Sorry, I should say, no, you will always take a equals 1, not just pretty much. In which case, when you compare the two statements of the factor theorem and your equation, you make this equivalence between the inside of the brackets. The negative b over a is the same as the 1. If a is also equal to 1, then all you're left with is negative b is equal to 1. B is therefore equal to negative 1. You have your a and your b. You now have the linear that is a factor of your polynomial. From there, if the question tells you to solve, then you would go through, do your whole polynomial division process to get the other factor, and, well, take it from there as is necessary. That's factor and remainder theorem. How are we going on that? Any questions so far? Cool. Okay, next up, exponentials. So first we'll look at how to solve exponentials, and then we'll look at some of the basics around graphing them. There's 3 main techniques that you can use. The logarithms one we'll look at later. Mainly you're going to be looking at either equating exponents or using a quadratic solution. The equating exponents thing is kind of similar to like beginner polynomial stuff, where you had a quadratic equals another quadratic, and you would just sort of look at each of the terms and make them equal to each other because they have to be the same thing. Same thing over here. There's an equal sign between these two statements, so we're going to essentially try to rewrite both sides of that equation so that they look the same. And in the case of exponentials, you want to convert the other side to have an index of some sort, have some sort of power. So you're going to be good at your powers of numbers to know what this will immediately simplify into. So basically, I guess the other way of phrasing that would be know your roots of numbers. I guess it's not really roots, it's a bit harder than that, but anyway. Yeah, so you figure out what the base power is, the base and power is rather, and then because the bases are identical, they will now have the same power, so you just go left to right and, well, simplify whatever's left over. In a more challenging example, the power might be more involved. You're still making sure that you have the same base for your exponential. In this case, 25 is 5 squared. And then you just got to be a bit more wary about your index laws, or at least a bit more refined with your index laws, knowing that this 2 distributes through rather than just like adds on, for instance. Then again, same bases. That means the powers must be the same as well. Simplify, simplify. That's the equating exponents approach. It's useful for these simpler solutions when you have maybe 2 simple exponentials or just 1 exponential and a constant. These are the kinds of things you would use this one for. Any questions about that? Okay. In a SAC, the likely thing you'll get will be one that requires a quadratic solution. So what we do here is we use this and we have a more complicated string of exponentials and constants in there. Some of the things to look for would be descending powers of x. We've got 2x down to 1x down to no x. The other thing would be coefficients that can't be easily simplified. And if all else, just look at the thing, and if it's super complicated, you're probably going to use a quadratic solution for it. There's a whole bunch of steps here, but whatever. We'll just see what they look like in the example. First things first, try to rewrite all your exponentials to have the same base. This is already done. You can extend that further and not only make them have the same base, but have the same basic exponential itself. Like for instance, this is 3 to the x, this is 3 to the 2x. If you really wanted to, just for your own clarity, you can knock that 2 off of the off of the x and rewrite it in a slightly different way. You don't have to do that, that's just for clarity, for your understanding of the substitution that we'll be doing. So basically, once you notice that 3 to the power of x is a common factor of both of these terms, you can do a substitution to make that look a little bit simpler, and then recognize that what you're left with is actually a quadratic. Again, technically you don't need a substitution. This already can be solved with a quadratic solution. This is for clarity. So once you get really good at this, you probably won't even do this substitution step, but to be honest, even I still do this, so you're probably not going to be graduating from that anytime soon, unless you want to risk, any stupid errors. But okay, that's just a quadratic. Solve it as you care for, whether it's factorization, quadratic formula. There's always going to be a solution here. You're not going to have to worry about whether there's no solution. What you will have to worry about will be whether the resulting exponentials have both solutions. There's going to be at least one. I've never seen a case where there's none. But essentially, because you've solved these in terms of a, you're not quite done yet because you're actually trying to solve for x. So all you do is you plug in what a actually was, the 3 to the power of x, and from there, from there you've just got two basic exponential equations that you can work with. 3 to the power of x equals 3 is going to give you x equals 1. 3 to the power of x is equal to negative 9 has no solutions. And the reason why, very basically, this is what the graph of 3 to the x would roughly look like. I know it says 2 to the x here, but the base is only going to mildly change that. The very basic answer is that there's no negative numbers on this graph, right? So there's no way this exponential will ever reach any negatives. The real mathematical reason is more of an exploration. For instance, if you were to choose any positive x values, you would only go up and up and up in numbers, right? Like 3 squared, 3 cubed, these are all bigger numbers. If you choose any negative numbers, you're just doing the reciprocal, which I can show here, right? Like if you choose any negative powers, you're actually getting smaller numbers, yes, but they're getting, in this case, they're halving. In the other case, it would be compounding as a factor of 3 every single time. But point is that we're not actually ever hitting negative here. We're just getting bigger and bigger denominators, which is why it's going to asymptote at 0 rather than ever jump over to negatives. And any of the fractional numbers, I mean, those sort of get a bit weird because now you've got essentially roots in the power. But yeah, those are the main reasons why you can't have a negative solution there, or at least have it equal a negative number. We talked about this. Yeah, I mean, that's about it for the quadratic solution approach. I noticed, Nihal, you've joined somewhat recently. I don't know how much of that made sense. I'm happy to explain in more detail if this is your first time seeing it. Is there any questions as to what I've covered so far? This is a catch-up lesson, so I was going at a bit of a faster pace. And let me know either way. Oh, there you go. All good? Yeah, nice. Okay, so graphing exponentials. I already showed you this. The basic graph of the exponential is this. It has an asymptote at y equals 0, and it'll curve up and to the right, basically. Now, the exponential is a bit of a special type of graph because not only does it have the same transformations as every other graph, your dilations, reflections, translations, but one other thing that also plays a role in your exponential is the base. Right, this base of 2, for instance, will behave slightly differently to a base. I mean, yeah, even a base of 10, right? Changing this number will also change the shape roughly. But where you get a more drastic change is when the base goes between 0 and 1. Suddenly, you get what is essentially a flip across the y-axis. It is another way to reflect in the y. The reason why it does that is sort of based on, again, we can explore it. So for instance, because our base is a half in this case, any increase in power is only ever going to actually make that fraction have a larger denominator. you're essentially getting the reverse option, or the reverse behavior from what we saw when we had a base of 2. Raising the power to more positive, so going right on the graph, has made it so that the fraction has gotten bigger. Well, bigger denominator, anyway. And then the opposite is true with the negatives. So going left, negative x's, suddenly because you have that negative index, you're flipping this fraction into a whole number and then multiplying it by the index, or applying the index, I should say, which is why we're now flipping to whole numbers here. They're getting bigger and bigger over time. The opposite effect has been achieved rather, and suddenly you've got what is effectively a reflection in the y-axis without actually having any negative signs in there. That's the worst part about exponentials. It's also the part that barely comes up. So that's kind of nice to know. It might come up in a SAC. I can't really promise anything for SACs, but exams, I don't think we've ever seen a base between 0 and 1 in an exam. Yeah, I don't think so. Anyway, just for clarity's sake, is there any questions about how or why that's working out? Sweet. Dilation factors work the same as they always have. If you multiply at the front, you're just going to stretch it along the y, or you could also say from the x. Essentially, it's getting the y values that you would have had have been multiplied by this number. So this would have been 2 to the power of 1. It's now 3 times 2 to the power of 1, which is why it's going up. The y values are bigger. You can also have dilation factors in the attached directly to the x. Just keep in mind that in this case, technically 3 is a dilation factor here, and this would be a dilation factor of a third, specifically along the x or from the y. That sort of takes us back to some transformation fundamentals, where the x stuff is always appears to be a bit backwards. Kind of like how subtraction in x makes it go right and plus makes it go left. Division is the default for the dilation factor in x, and multiplication you have to then flip it to reveal what the actual factor is, which I've written a basic note here. You don't need to know that too much unless for whatever reason you're getting exponentials in your transformation stuff, but usually transformations, I mean, if we have a look at where it is in the textbook, it's covered well and truly before we get into any other stuff there. But you might get it anyway, in which case that's something to worry about, not just for exponentials, but for other things. Anything that has like an x dilation, for instance. Reflections, those are fairly straightforward. They work the same way. I think the only thing to watch out for in exponentials is because the x is in the power, it's not like you're looking in a different spot for your x transformations. Essentially anything that's applied in the power would be considered an x transformation. So when you're looking for anything affecting the x, yeah, it's going to be in there in the power. Reflections are also a bit weird because now that negative signs can also be applied, you now have a bit of a push and pull between what your base is and then also if there's any negatives applied. So for instance, if you have a basic 2 to the power of x, negative 2 to the power of x would shoot it down. But if your base was between 0 and 1, it would normally go up and left, so now it's got to go down and left. So you can see the green is essentially where we're starting, and the blue is where we end up. In both cases, you're flipping down. It's just a matter of what your starting point was based on the base. Same thing over here. If the negative is in the power, then it's a reflection in the y. So yeah, the y values are maintaining their value, but the x, where it's located horizontally, has changed. Translations, again, so horizontal, anything plus or minus on the x is going to be in the power. So when you have x minus 2 in the power, you're technically shifting that right. I will mention that the horizontal translation doesn't really matter a whole lot for exponentials. You can see if you were freehanding this, you're basically drawing the same curve. The only thing that's going to change is what number you put on one of your axes intercepts. and that'll just come out in the math rather than you making a deliberate decision to put something somewhere. It's not really like a turning point in quadratics, for instance, where if you look at your horizontal and vertical, you know where the turning point is. This translation doesn't really tell you much. It doesn't help you put a key feature on the graph, for instance. But the vertical one does. The vertical one is directly tied to your horizontal asymptote. So we knew it originally had a horizontal asymptote at y equals 0. When you now have a plus or a minus at the front of the equation, or the back, however you want to think about it, even though the exponential term is getting infinitely closer to 0, you're just always adding 1 or subtracting 1 or whatever the number is to it, which is why the default is now shifting. That's a bit more like the math as to why it is the case. The basic that you need to know is just whatever the plus or minus is at the back, that's your asymptote. Yeah. In simpler cases like pre-logarithms, you'll pretty much never have an x-intercept. The reason why is because in a lot of cases that aren't like specifically tailored for pre-logarithms, it'll be a lot more complicated. You have to do this conversion between exponentials and logarithms. If you haven't explored that as of yet, don't worry, we will do so in next week. It's beyond the scope of what we're looking at here. So x-intercepts just aren't going to come up until you look at logarithms. The other thing that will come up will be the y-intercept. So basically the two things you're looking for are going to be your asymptote, which is the plus or minus, and the y-intercept, which is always just subbing in x equals 0. It's the y-intercept specifically is pretty easy because you can see that you're essentially going from this to this in a single line. Like it takes no effort there. Any questions on the fundamentals there? Okay. Here's the steps you follow, roughly speaking, for when you're sketching exponentials. I'll start with a nice and messy one, just so you can see how each of the terms will play a role in what's going on. It's good practice to start any sketching by rearranging into the general form of whatever the function is that you have, or in other words, just making sure you can clearly see what are all the key transformations that matter. Like for instance, because this is factored out as a -3, it makes it kind of hard to see what actually is this. There's no plus on the outside of the function. There's a whole multiplier on everything. So we can't clearly see what the vertical translation is until we expand it all the way through, which we do here. It's at this point you could probably stop. You don't have to go this step beyond, because I kind of already mentioned that that horizontal translations don't really do anything beyond the math of how you would solve things. So really all you really care about here is going to be the +1, which gets you your asymptote, and this negative sign, which will play a role in reflecting the graph. The basic exponential goes up and right, as long as it has a base greater than 1, of which e does. So e is a special number, kind of like pi. It's roughly 2.7. All you need to know is that the e graph is up and to the right. So this, by default anyway. But because we had a negative, we had a reflection term here, it's going to now go down instead. From here you solve the axes intercepts. Don't worry too much about getting this x-intercept. It's got logarithm stuff in it. The ones that are made for pre-logarithms will basically boil down to this, which you'll typically be doing by equating exponents. So it'll be just as simple as that in what you'll actually see. Once we get to logarithms, you might come across stuff like this. But you can see even just briefly, 1, 2, 3, 4 lines of working to get your x-intercept. So it won't actually end up being all that bad, even if you haven't seen this before. The y-intercept, even easier. You can see we're just shoving in a 0 there, and then, well, cool. -3 times 2 is -6. That's all we got to do. That's all that's left. And that is just your y-intercept. There's no further simplification to be done. So you draw out your curve, you draw lines through the key features, just like you have for all the other graphs. So asymptote. I just noticed it isn't even labeled on here. Dear God, there should be a label of a y equals 1 there. Then you label your x, your y. Those are the key features you need to have for that graph. Yeah, I think that's about it. Any questions on that? All right, cool. So let's see this planner that I was sent. Domain range, properties of functions, power functions, transformation equations, transformation graphs. Yeah, okay. So I think the most relevant thing here is going to be the, well, technically none of it, I suppose, but transformations. Yeah, okay, cool. Is there anything, because that does seem a little off topic, is there anything in here that you guys specifically want to have at least a touch on before I get into some newer stuff? I know we have done this stuff before. Any of those that we should touch on first? I'll definitely have a look at the newer stuff. But just while it's fresh here, is there anything we should have a look at? Cool. All right, Taihan. Well, I guess we'll go from there. There's a lot of stuff you've given me there. Was there anything in there in particular that you felt was worth focusing on the most?
Probably the transformation stuff. I'd say I'm like mostly like confident, but like it would be really good just to kind of go through the textbook and just to go over it
Yeah,
if we have
sure.
time.
Yeah, we'll have a look at it. Cool. Transformation equations, 3ADE. Oh, this is the wrong book. 3ADE. Have you already had a look at, like, have you tried some of the questions in your planner? Do you know where?
Yeah, a few of them, yeah. But I just thought it would be helpful just to revise it. Just because it wasn't taught super well at school. So
Yeah, okay. I guess I'm just trying to figure out where to start. Do you want me to just do top to bottom on it, or?
yeah, I think that would work out. Just because yeah, the test is basically just going to be based off those sections.
Yeah, okay. Cool. All right. So transformation is 3A. You've got question 7 as one of the things to have a look at. Find the equation of the image after this stuff. Cool. All right, so what I'll do, just so everyone can be on the same page, is I'll drop my notes for transformation stuff as well, so we can follow off on that. In the meantime, if you guys already are confident, we're having a look at 7A on this one. So feel free to make a start on that while I grab up the transformations relevant stuff. Alright, if you want to have a look at my notes on how we do transformation stuff, then that's in the chat now. It'll, at least for this one, it'll be document 1 in that list. Okay, cool.
Chris, I think you sent the files in the DMs.
Oh, I sent in the DMs. Thanks. Cool. Alright. That'll be better now. Okay. To start us off, how might we go about doing question 7A? Oh, by the way, Nihal, I've got another camera that we do the work solutions off of. So if you pop off the screen share, you'll notice one of them is pointed at my phone. If you just pin that, so right click it and pin, you'll be able to easily swap between the two screens. Easy. All right, cool. So 7A, we've got a quadratic. The translation is described as mapping x to x minus 3 and mapping y to y plus 2. We'll start writing that out. As I'm going through that, let me know if there's anything we should do to start it off. a bit on the unusual side for transformations to actually be written like this. Usually they'll say it in words. Oh, hang on, got a question. Can't seem to access this. The PDFs. It's a bit weird. They should just be files. What happens when you click it? Yeah, okay. I'll send it to your school chat instead. So the platform that you signed up on, I'll send a copy there. Should be able to grab a copy from that, surely. All right, they should be sent there. So if you just pop back over to the platform that you joined, that'll be in your chat box. Anyway, okay, cool. So one of the recommendations I can say here is noting that this is your x dash and y dash. So any set of transformations can be described by saying the following: xy maps to x dash y dash, where x dash and y dash are the new x and y. So this statement here says x dash is x minus 3 and y dash is y plus 2. That's what that actually tells us. Hopefully that should help kickstart. Because that'll put you specifically on, if we look at document 1, yeah, I mean that gets you step 1, which is getting your x and y dash equations. Yeah, I'll keep on the screen share. I'll have the procedure that you follow. In fact, it'll probably be even easier if I show one where it's got the work solution to it. Yeah, something like this will do. Maybe, yeah. That'll be perfect, actually. If you want to refer to the screen share on this, it's very similar. What you follow, we've effectively completed step 1, the equivalent of step 1 for this.
Would it become x minus 5? Because when you're minusing from x, it increases the.
Would it become x minus 5? Well, we finished step 1, so where did you get x minus 5?
When you have the x minus 3 with the x minus 2, or?
Okay, so you're going directly into that. Understood. There is one step you didn't do. You skipped over step 2 in this case. You want to rearrange to get the x and the y on their own first and then shove it into the function. So currently we have dashes on these, x dash and y dash. You want those to be out of it. So what you want to end up with instead is x equals x dash plus 3, y equals y dash minus 2. You now have x and y on their own. Now you can go through and replace every x with the x plus 3, every y with the y minus 2. So in order, step 1 is, well, step 1 was literally just reading this and then putting it into equation form, knowing that this thing's your x dash, this thing's your y dash. Step 2 was get the x and the y on their own. That's basic algebra. Everyone can do that. It's just a matter of knowing to do that step. And then the last thing is also basic algebra. This thing is y, this thing is also y. So replace it with what you got, y minus 2. This thing is x, this thing is also x. Substitution. X plus 3 minus 2 all squared plus 3. And again, we're just doing algebra here to get the y back on its own. Y equals x plus 3 minus 2 for plus 1. all squared, and then plus 5. That is what you did mean to put it in here, right? Because we did end up with a plus 5 in there. I just want to make sure I didn't.
Yeah.
Yeah.
Wait, so just to confirm, we've got the equation y equals x minus 2 squared plus 3, and then you just map it out as x dash, and then what the transformation is. Like x dash equals the transformation,
Mhm.
and then y dash equals the y transformation.
Yep.
And then rearrange that equation, that specific equation, so that the x and y is by itself.
Yep.
And then you take the original equation and then substitute in for what like includes a y dash. So the x becomes x plus 3 and the y becomes y minus 2.
Perfect. That's perfectly described. Yeah.
Okay. Yep.
Nice.
Cool.
All right. Let's see if we can apply it. Because where's the planner again? It's all of 7. Nice. I mean, I guess it is similar. All of 7's basically the same. All of 8 is a bit different. We'll do at least one more of these. Yeah, we'll even keep it as quadratics as well, so it's even more similar. So we'll look at part B for this one. Y equals 2 bracket x plus 3 all squared plus 3 x y maps to x plus 3 y minus 3. All right, when you're ready, who wants to walk me through this one?
So you just have x dash equals x plus 3, and y dash equals y minus 3.
Perfect. X dash is this thing, y dash is this thing. Just reading. Nice.
Yep. Then... and then rearrange so that the x and y is by itself. So you would have x equals x dash minus 3. And then y equals y dash plus 3.
Perfect. Yep, exactly as you said. Rearrange to get the x and the y. I'll expand a bit deeper as to why. This thing says y. So to do a substitution, you need another thing that also says y. Same thing with x, right? If you chuck an x dash into an x spot, they're technically different variables. And so that's why we have to do this rearranging step if we're going to shove it into a function. But cool, okay. That is part of what you have to do, so that's good.
Yep. And then when you substitute in for the, I guess, let's say new x and y, you would get y plus 3 equals 2. And then in brackets, x minus 3 plus 3, which I
Yes.
guess you can just cancel out now if you want. Plus 3 at the end.
Sweet. All right, what are we going to end up with?
So you can first minus 3 from both sides.
Yep.
So you would get y equals 2 times x squared. So yeah, y equals 2x squared.
Yeah, everything basically cancels out there. Sweet. And yeah, at this point, this is just algebra. Simplify to get y on its own.
Yeah.
Cool. All right. That's fair then. So that's the same thing with all of the rest of 7. Yes, they're different functions, but all that's changing is where the x is located. Even the y is in the exact same spot every single time. It's just, oh, cool, the x is in a denominator. Oh, cool, the x is in a root. It's whatever. It might as well be somewhere else self-contained.
How would it work with C and E, or like E specifically? Like, what would be the processes for C and E?
Yep, okay. So I don't even have to look at the function until the last step. So always starting with the x dash is x minus 1, y dash is y plus 1, rearrange, and then whatever you're left with, so this will be x plus 1 after the flip, you shove x plus 1 in the x spot, you shove y minus 1 in the y spot, rearrange. I'll do that now. So we had from that, I'll just sort of skip a step real quick and do the x dash. So x dash was x minus 1, y dash was y plus 1, The next step is always rearrange. So x equals x dash plus 1, y equals y dash minus 1. In fact, this might be helpful for you as well. We always have some function y equals f of x. So in the most generic possible circumstance, every y gets replaced with, in this case, y minus 1, and every x gets replaced with x plus 1. So whatever the function is, every instance of x is now x plus 1, every instance of y is now y minus 1. So generically, for all possible functions, this set of transformations now looks like this. So literally whatever I write my f of x as, it doesn't matter how many terms are in there. Every time I see an x, it gets replaced with an x plus 1. Every time I see, well, I guess I also just chuck a plus 1 at the very end as the final thing. So in this case, our f of x is the cubed root of x minus 3. And we got a plus 2. Based on what I've said so far, what's our new function going to look like? Anyone?
Is that a cube root or a square root?
Cube root, yeah. It's going to be
Okay,
the
so
same
it'd
either way.
be y equals the cube root of x minus 2 plus 3.
And then plus 3. Yeah, so plus 1 and plus 2 combine to be plus 3. X plus 1 and minus 3. The plus 1 and minus 3 combine down to being minus 2. Yeah, that's it. So, whatever I give you as f of x, I mean, f of x could be something super nasty as like 1 over the square root of x minus 3 all cubed, and then plus, I don't know, some exponential. Every x is just going to get every x is going to get x plus 1, and then you're just going to chuck a plus 1 at the very end on that mess of function stuff. Clear enough on what's going on there?
Yep.
Part 8 is, let's have a look, what's 8 even saying? State a transformation which takes us from the first graph to the second graph. A transformation. Okay, so the fact that it's using the singular A transformation, the nuance around that would be probably that they're expecting your xy maps to x dash y dash notation, because you're explaining the set in a single statement versus a sequence of words. So for question 8, this is the second document. This is the determining the sequence. You're going backwards rather than knowing it and then applying it. You're now going from not knowing what it is and then figuring out what it is. So we follow these steps to do that. It's been a little bit since we've had a look at this. Let's see, how should I do this? I'll write out the actual question statement. So we're going from y equals 1 on x squared, and we're mapping that to, it is going towards 1 over x minus 2 all squared plus 3. Okay, so that's the goal. We're trying to get from one to the other and write that as a sequence, although technically speaking, this one here, you'll stop at question 3. You got a question, Tyon? Or is that a...
Yeah, I was only say for this situation, you're trying to find it from y equals 1 over x squared to that equation. But if it was asking you to go from the other equation to y equals 1 over x squared, and you feel like it's easier to go from the simpler equation, would it just make sense in the exam to figure it out the other way and then just reverse, obviously, because just find the opposite of the translations? Do you kind of get what I mean?
Yeah, I get it. Yes, but order matters. So
Yeah.
one of the things we had to look at was the order in which you wrote transformations mattered a lot. So I haven't done it that way, but just sort of spitballing. If you determine a sequence that goes from the second to the first, not only, yeah, get that in the right order, and then reverse that exact order. Reverse that exact order. Yeah.
Okay. Yeah.
That's how that would work.
How do you determine in step, I think it's step 3, whether you're solving for x dash or just x?
It's always x dash y dash, because by definition the x dash y dash is the transformation itself. Like if we looked at back to the handwritten bit that I was doing, the very first statement was we had a mapping of xy to some new x and some new y. That right hand side of that equation, that mapping statement, those are the transformations. So you're always trying to get your x dash y dash, because the goal of this is to figure out what transformations am I needing to go from one to the other.
But then in the step below, you solved for just x and y. Whereas I've also been doing some equations where the step above would be like the question format would be in some regard different, but you would be solving for the x dash and y dash. How do you know which equations you solve which?
Yeah, okay. So it does boil down to what the question is asking for. So even if we just look at the screen share steps that I've outlined here, the goal of step 3 here is to figure out what the transformations are. Just in a nutshell, with basic x dash y dash, going from one to the other, that's the goal of step 3. In some cases, like in the question we were about to do, that's where you would actually end it, because it's asking for the transformation. If it wants it in words instead, then you move on to step 4, which is, yes, we're doing a bit of rearranging in this case, but it's simply to make it so that when we say the things in the right order, we are in fact saying them in the right order. This is more of a clarity thing for when you have to put it in words. This isn't stuff that's like necessarily mandatory. It's there to make it as easy as possible to look at this thing and then put it in words. Because technically speaking, as soon as you hit part B, you have in one line described the set of transformations that's required. It's only if you need to then put it in words that you move on to this bit here. So that's one little thing to touch on between whether you're doing x dash y dash and whether you're doing x and y. The main thing is if you want to get if you need to find the set of transformations, you want to find x dash y dash, because those are the same thing. X dash y dash are the transformations. If you want to find the resulting function and you know the transformations, so you're literally told them, then you need to get x and y, because functions work in terms of x and y. You want to shove those into the function itself and then rearrange whatever you get afterwards. So in order, basically, if you want to find a new function, you want to get the x and y stuff. If you want to find the transformations, x dash y dash. Is it clear enough, the differences there? Cool. Okay. Yeah. Where was I? Okay, yes. So we're now working on the opposite, which is we're told function 1, function 2. There's no ambiguity as to what the functions are, so we know those already. What's unknown is how we get there. What I have is like the steps here will basically get you there every single time. I will say those are kind of heavyweight as well. Like for instance, before we even dive into the notes that I have here, if we just look at what we're looking at here on the handwritten bit, it's a basic truncus mapped to a truncus with 2 translations. All right, it's shifted right by 2 and up by 3, if you guys know the basics of the truncus. And so, because it's as simple as that, if all you're required to do is the bullet points, just say that. Like if you can see it quite clearly and there's no complications around it, there's no real need to go through all the stages here. The steps that I have outlined are best used for when you have so much stuff in there that it's kind of hard to know what order you do them in. But this is a simple enough one to where you can actually just see them. Now, where you might get caught is if you're trying to do it in terms of x dash y dash notation, because if you just say x, y maps to x minus 2 comma y plus 3, you just got to remember that x dash and y dash in transformation notation, you have to be, you essentially have to reverse what you've already reversed in x. Or in other words, shifting right does in fact show up as a plus in x dash y dash land. And left does in fact look as a minus. That's the only thing you'll get a bit weirded out by if you have to do it or if you try to do it this way. All that to say, there are shortcuts you can have a look at for this sort of stuff. Once you get really confident with going through the whole procedure, these are the sorts of things you would want to look for to make sure you're not spending too much time in stacks. Is it clear enough, both ways of looking at things? Okay, cool. So at least we already know at this point where we're trying to head to, which is we want to make sure that we're shifting right by 2 and shifting up by 3. How we get there is just, well, how we want to get there. There's so many ways to do it. I've actually even got 2 in the same document. You can do the point version, or you can do the function version. Point version is typically what people will most be most inclined to do. So let's see if we can walk through that. Step 1 is to figure out where are we starting and where are we going. What's the original function? What's the new function? So I've got that highlighted up on the screen share if you want to follow along the step-by-step. Essentially, all we're doing here is notation. We're trying to figure out what's going to get our x and y notation and what's going to get our x dash and y dash. The new thing is always the thing that we're heading towards, and it's always going to be x dash y dash because that is the new thing by definition. So if we go back to the handwritten bit, the original function, y equals 1 over x squared, is going to stay with y and x because it's our original function. Our new function, because it's new, is going to get the dashes. So y dash and x dash. All we're doing is rewriting what we have. From there, step 2, rearrange the transformation factors affecting the y to the left hand side, and the transformation factors affecting the x are going to stay on the right hand side. So you do this for both functions. You look at this one here, you look at this one here. Any transformations affecting the functions, both of them should be rearranged. As far as how you do that, the simplest way to do it is to shift over as much as possible until the graph stops looking like what it should. Like for instance here, if I shift over the 3, what I have on the left hand side still looks like a truncus. There's nothing else. It still looks like a basic truncus. What I wouldn't want to do is expand out this square or square root both sides, multiply, because suddenly it's now looking like a function that we can't really, we're transforming it into a completely different looking function. So the basic rule is get all the y stuff on the y side, and if you're ambiguous as to what the y stuff is, just move enough over until it stops, well, just before it stops looking like a function that you're used to. Clear enough on what to rearrange? Cool. Okay. Step 3, write the expression. So mapping the xy to the new x dash y dash. The way we do that, we have these 2 functions now. So all we're doing is making the left-hand sides equal each other and the right-hand sides equal each other. That's all we're doing. I won't even bother mentioning the shortcut here because I think it just confuses people. Y is the same as y dash minus 3. Y equals y dash minus 3. Left equals left. Same thing over here. Right equals right. 1 over x squared is equal to 1 over x dash minus 2, all squared. Part B of this is to get the x dash and y dash on its own. We're trying to find transformations here, and because the transformations are the thing that's unknown, we need x dash y dash because x dash y dash are the transformations. For the y, it's very simple. Y dash equals y plus 3. Done. For the x, there's a bit more going on. We could start by square rooting both sides. 1 over x is 1 over x dash minus 2. Cross multiply both sides. So multiply this one by x dash minus 2 and multiply this one by x. And then finally getting the x dash on its own. That, for the purposes of this particular question, is actually it. It said find a transformation. There is no English way to describe this in a single transformation. This, in English, if you were to say it, would be a shift or a translation up by 3 and a translation right by 2. Two separate things. You can't say that in a single sentence. So because they've said to say it in a single statement, and I'll show the wording on that on the screen share, state a transformation, which maps it, not multiple, the only option you have left would be to use the xy notation. So you do xy maps to x dash, which we know is now x plus 2, and y dash, which we now know is y plus 3. That is the only way to do it in a single succinct statement, which is my reasoning for why we have to use that notation. Fair enough on what's going on there? This will be the hardest bit of transformations, which is the determining the sequence, right? This particular question that we're doing is the harder bit. Cool, okay. We've covered a lot of transformations in previous classes as well. So if you guys want to review the recordings on those are in the past recordings tab. You'll notice that each of the weeks has a subheading rather, for what's covered in that thing. Feel free to skip around to find the parts you need. Alternatively, there's also the classroom content as well. So this would be under functions, relations, transformations. And the two documents there have accompanying videos as well that are not class recordings. Those are like direct-to-camera scripted things. So I've gone through the key questions in, well, as much clarity as I could script out specifically. Should be fine though. Yeah, so a bit of all over the place for this one. Thanks for covering. Yes, no worries. Happy to help. Yeah, so I guess it's worth putting out the format of this just as a reminder for anyone who's who has maybe either forgotten or needs a reminder of the format. We'll typically go through class the syllabus content only if people don't have any particular recommendations for what to have a look at. And the reason why is, I'm sure some of you will be aware, like, you guys might not be doing exponentials right now. What the syllabus is based on that I've got here is what most schools are doing at most times. And yeah, that helps a lot of the time. But if you guys have things that are coming up, like I believe you said it was your SAC that was coming up, more than happy to dedicate some time towards making sure you're getting something out of the class rather than studying ahead when it's kind of whatever. So there is a bit of flexibility in the case where you guys want to actually have a look at something in particular. Ideally, you submit that stuff ahead of time. That way I can prepare a particular thing at the start of the class. There are Google Forms links on each of the class things for you to have a look at to submit stuff there. And that way I can maybe even have like prepared questions and stuff like that. But this is fine as well, right? Cool, all right. I've exhausted the last minute that we had. If you guys have any further questions, I'll stick around for a bit. Otherwise, yeah, thanks for coming.
Thank you.
No worries.
Yeah, I guess I was just wondering, like, obviously based off that planner that I sent you and kind of what's going to be assessed, what you would say is kind of the best way to go about revising or preparing.
Yeah, okay, what's the best way to go about it? I mean, definitely doing all the questions there is ideal, making sure you've touched all of them and are confident with all of them. Chapter review stuff, I would say that's probably the more let's see, how do I phrase this better? Chapter review stuff is typically the harder stuff especially the extended response versions of those. So if you're going through these questions, like for instance 1C, domain and range, if you're looking at that like, okay, this is stupid, I've done all these, I've got the last 6 of them in a row right, then just move on to the next thing. Once you've got all the individual chapter section stuff down to a point where you're like, yep, okay, I'm getting enough of these right, I'm not losing any marks or stupid errors, then the primary focus becomes a chapter review, extended response stuff.
Yeah.
I believe each of them will have an extended response section in there. If you run out, I believe, do you have Jacaranda book as well?
No, I think I have the Cambridge one.
Yeah, like I know you have Cambridge, but okay, you don't also have Jacaranda. What I'll do is, do you think you'll run out of?
Sorry?
Do you think you'll run out of chapter review questions?
I mean, I think there's quite a bit in there. I think that should be enough. I'm not sure.
Okay, well, I'll chuck in the Jacaranda stuff anyway, so that doubles your amount of questions in there. Yeah, it'll look a bit different, but it's the same questions.
Yeah.
Okay, that should be in there as soon as it loads up. Those are big beefy books though, so it'll take a bit of time to load up. So just hang out for a sec while it loads.
All good.
Maybe I should send it off Zoom actually, because this is using my data. Well, not my data, but my it'll use some internet bandwidth. Maybe I'll send it to your chat instead. Yeah, some of them crashing. Cool. I'll get that sent to your chat on the on school. Yeah.
Okay, cool. Sounds good.
Easy.
Thank you,
All right.
Chris.
And yeah, you can
Bye.
reach out if you have any questions as well. Feel free.
Yeah, sure, we'll do. Thank you. Bye.
Take care.